Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing on our final week of lecture together, virtual lecture? Hopefully everyone's doing well. So on Friday, we had our virtual ECS Showcase. So for those of you who had senior design project to present, I just want to say, just for myself, you guys should be really proud of the work that you've done. I know it's been really challenging this semester to complete those projects, and I think in a lot of ways, a little bit, disappointing in that you can't kind of realize a lot of your projects in real life. But given the circumstance, I can see that a lot of you have worked really hard, and I think that really showed in what you can show on Friday. So I wasn't able to come to everyone's presentation just because a lot of them were going on at the same time, but the ones that I did see, I was very, very proud of, and I tried to go to as many of the presentations of the students in my class as I could, but then I'm not sure where everyone is. So but great job for everyone. Okay, so the plan for today is that we're just going to finish up our lecture notes on unsteady finite volume problems. So we don't have that much to go, so I don't expect this to take up the entire class session. So probably it might take up maybe 45, 50 minutes, just because we're a little bit ahead of schedule from where we were. Okay, and then after that, we're basically going to be done with the class. Okay, so I just want to clarify a few things before we begin. So I've got some questions about what's going to happen next week, and the due dates and everything. So I just want to say that there's still no final exam in this class, so we're not going to take any more exams. So the only things you guys have left to turn in is homework 6, which is going to be due this Wednesday. So I know a lot of you guys have been working on that already, and I've gotten some questions on that. And then there's going to be the final project, which is going to be due 2 weeks from today. So it's not going to be due next Monday, but the Monday after that. So it's the week after finals week. So that's mostly just to give you enough time to grade everything. Okay. Okay. So are there any questions about homework 6, or just anything in general before we get started today? So for homework 6, there was a typo on the solution for 2a. So I kind of divided by a number instead of multiplying it. So it changed the answer somewhat. So someone pointed out to me over the weekend, and then I fixed that. So then that should be there. Nicholas, I don't think I saw your project. So actually, if you want to send me your slides, the ones that you presented, I'd love to see it. But I don't think I got a chance to see yours because I wasn't sure which one you were working on. But I saw a lot of the I saw a lot of the groups that were working with Edwards Life Science, since I've been working with some of those groups. I saw a lot of the student projects, like I saw the formula, I think the formula team, and then I saw some of the ones in session 4, I think it was, near the tail end. But I didn't get a chance to see yours. So send me your slides. Yeah, I'd love to see what you've been working on for your senior design. Okay, so let's go ahead and get started today. So we're going to pick up where we left off last time with unsteady finite volume problems. Okay. So just as a reminder, let me write out kind of the form that we were working on. So remember, with unsteady finite volume problems, we're kind of solving the whole shebang here. So our equation looked like this. Okay. So we had our time derivative term, because we have unsteady problems. Okay. Next, we have our convection term. Okay, so our convection term is given by this. Right? Then we have our diffusion term. Okay. Then of course we have our source term. Okay. So that's what we were working on. So then after we applied our finite volume method to this guy, so we integrated this, applied all of our integration rules, divergence theorem, trapezoidal rule, and everything like that. And since where we left off was with an implicit solution, we were left with the following expression. So I'm going to start, like the expression I'm going to start with is something halfway, just because it'll help us kind of with applying the boundary conditions. Okay. So the form I'm going to give you is the form of this equation after we've evaluated each of the 4 integrals. because remember we have our integrals on the north, south, east, and west side. So I'm going to keep it kind of in that form so that when we start to apply boundary conditions, we can just go ahead and replace them right there. Okay? So let me go ahead and write this form. Okay? This is after FVM and implicit Euler. Right? So then that gives us the following expression. So we have phi at C n plus 1 minus phi C at n, all divided by delta t, okay, times delta squared, where remember the delta represents our spatial grid size. So in this case, we've already assumed that delta x is equal to delta y is equal to delta. Okay? So this term, remember, this comes from d phi dt, okay? Plus, then we have our east integral. So our east integral is given by the following. So we have u over 2 times phi at big E plus phi c minus k over delta times phi e minus phi c all over delta. Oh, we've already divided by delta, so we don't need that again. Okay. Okay. And then all this is multiplied by delta. Okay. So this right here, this is our east integral. Okay. So when we apply boundary conditions, we're just going to replace this entire expression for with that with the our boundary condition. Okay. So that's the east integral. So now let's do the north one. For the north integral, we have delta multiplied by v over 2 times phi at n plus phi c, okay, minus k over delta phi at n minus phi at c. Okay. So this right here is our north integral. Okay. So then after this, we have the west integral and the south integral, which I'll put on the next page, just because there it's a little bit. Okay. Before I turn the page, are there any questions on this? So I'm kind of picking up kind of in the middle of the derivation that we started last time. Okay. So let me write this plus west integral plus south. Okay. Okay. Okay, so let me write out the west and the south integrals on the next page. Okay, so next we have minus delta times u over 2 times phi w plus phi at c, okay, minus k over delta times phi at c minus phi at w. Okay, so this right here, this is our west integral. Okay, and finally we have the south integral. So the south integral will be delta times v over 2 phi s plus phi sub c minus k over delta phi at c minus phi s. Okay. Okay. So there's our 4 integrals, where each of the integrals, they include both our convection term and our diffusion term. Okay. And then all of this is going to be equal to our source term. So this is going to be equal to q at xc yc delta squared. Um, so then later on, once we start to apply boundary conditions, we're going to basically modify this this expression by just replacing whichever integral is next to boundary. Okay. All right. Any questions on this? Okay. Okay, so then let's pick up where we left off with the example. Okay. Okay. So for this example, we have the following. We have d phi dt. Okay. So since we have a time derivative, we know that this this problem is going to be unsteady. Okay. Plus 50 cosine of pi t. Okay. D phi dx. So there's our x convection term. Plus sine of pi t d phi dy. So that's our y convection term. So this right here is going to be our u. It's going to be our v. Okay. It's going to be equal to 3 d squared phi dx squared, okay, plus d squared phi dy squared. So there's our diffusion term, where this 3 right here, this is our diffusion coefficient k. Okay. And then plus 3xy, which is going to be our source term. Okay. So I think last time what we did was we went over how to find the equation for the interior cells. Okay. So for the interior cells, we basically plug into that that kind of boxed equation that we went over near the end. Okay. So now let's go over how to apply the boundary conditions. Because for this problem, we had the following boundary conditions. Okay. Okay. So on the left side, we had phi is equal to 50. On the right side, we had phi is equal to 25. On the bottom, we had phi is equal to 25. And on top, we had phi is equal to 50. Okay. So basically, in this situation, we have Dirichlet boundary conditions all around. And just because we have an unsteady problem doesn't mean we can still apply our boundary conditions in the same way. It's just because we have that delta t floating around and we have this time derivative, it's going to modify the expressions for the coefficients a little bit because we need to make sure we include that delta t into our coefficients. Right? All right. Any questions on this? Okay. So let me since I think we're going to have some time today, so let me kind of redo the interior cells just so it's clear. Okay. So if we take that kind of long equation that I started with at the beginning, where I separate down to east and west integrals, if we kind of collapse all the terms together, we get kind of the plug and chug type of formula that you would normally be associated with these things. Okay. So let me write that out again. Okay. So we have u delta t all over 2 delta minus k delta t all over delta squared. Okay. Okay. And that's going to be multiplied by phi, our east neighbor, phi sub capital E at the n plus 1. So that's at the next time step. Okay. Because remember, we're doing an implicit equation. So we're going to have a lot more n plus 1 terms. Okay. Next, we have the coefficient for our north neighbor, so phi capital N at the n+1 time index. Okay. Next, we have the coefficient for the west neighbor, and then finally the coefficient for the south one. Okay. So those are all the coefficients. So remember, for this one, it's still the same equation that we started with up there. It's just I've kind of moved some of the terms around just so they're convenient kind of for plugging it. Because in this form, we can basically find the coefficients for each of the different neighboring cells, and also for phi sub c after I write it down. And then we can just extract those exact numbers. Okay. So that's the coefficient for the central cell. Right, and then we have the source term, and then because we have that extra phi sub c that comes out of the time derivative, we need to add that over to the right-hand side. Because remember, everything on the right-hand side is okay. So this is basically our unsteady FEM equations for the interior cells. So if we plug that into this equation, noting the fact that our convection velocities are functions of time, so our u and v's are going to be functions. They're not going to be just numbers. Okay? We get the following expression. So we get 10 cosine of pi t minus 4.8. Okay, and that's multiplied by our east neighbor. Okay, so that's phi sub e plus okay, and that's going to be plus 0.2 sine of pi t minus 4.8, and that's multiplied by our north neighbor. Okay. Okay. Then we have the coefficient for the west neighbor. If my stylus decides to work. Hang on. There we go. Sorry about that, technical difficulties. Okay, so that's our coefficient for the west neighbor. So that's minus 10 cosine of pi t minus 4.8. Okay. And then we have plus minus 0.2 sine of pi t minus 4.8. Okay. And that's multiplied by our south neighbor. Okay. Then we have plus 20.2 times phi sub c. Okay, so that's our self, and that's equal to 0.3 xcyc plus phi sub c to the n. Okay. So this is the interior equation that we kind of ended with, and you can apply this for any interior cell which has north, south, east, and west neighbors. Okay. So it's basically going to be plugging in. So I think what we did at the end of last lecture was we applied it to cell 6, where the west neighbor for 6 is 5, or maybe I'll start from the top. So the east neighbor for 6 is 7, the north neighbor is 10, the west neighbor is 5, and the south neighbor is 2. So you can fill in all those indices, and you can get those equations. And you can apply the same equation to cell 7, 10, and 11, because we have basically a 4 by 4 grid here. All right, any questions on this? Okay. Okay, so now let's do the boundary conditions. So we know that for this problem, we have Dirichlet boundary conditions all around. And unfortunately, Dirichlet boundary conditions are a little bit more involved to plug in or to apply in finite volume. So actually, I picked Dirichlet just to kind of illustrate. Okay. Right? So remember, when we're applying boundary conditions in finite volumes, what we're doing is we're replacing an entire integral expression with the boundary condition term. Okay? So let's say that we're going to have a cell that's on the west face. Okay? So this is going to be cells 1, 5, 9, and 13. So in this case, we have a Dirichlet boundary condition on the west side. Okay. And so what this means is that we're going to replace the west integral with the appropriate expression. Okay. Let's go ahead and do that. So our west integral looks like this. Okay. So integral on the west face of phi v dot n, okay, minus k del phi dot n, okay, ds. Okay. And then, as we always have with this integral, let's replace it with the Dirichlet boundary. So with the Dirichlet boundary, it's going to look like this. Okay. It's going to look like negative phi naught times u minus k phi sub c minus phi naught, okay, all over delta x divided by 2, okay, all multiplied by delta. Okay. And let me change this delta x to just a delta because we've assumed that they're equal. Okay. Clear this up. 2. Right. So in this case, delta naught or phi naught, this is our known Dirichlet value. Okay. And since it's known, it's eventually getting multiplied onto the right-hand side of the equation. Okay. Okay, so let's rearrange these terms a little bit. So then what we get from this is minus 2k phi sub c plus 2k phi naught. Okay. And so what we're going to do is we're going to take this and plug it we're going to plug that into the west integral into the kind of the first equation that we went over at the beginning. Okay? So the equation that kind of took up 2 pages, where I've kind of indicated the west integral, we're going to plug this guy in for that. Okay. All right. Any questions before I kind of go back to that page, just so we kind of see where we're plugging into? So let's go back to the beginning so we can see where we should plug it in. Okay. So remember, we after we applied all of our integration rules and our implicit time advancement, we have this expression here. So instead of, so everything else is everything on this page is going to stay the same because we're assuming we have an east neighbor and a north neighbor. So that's not going to change. So what's going to change is going to be this guy right here. So instead of this expression here with the west and the with the west neighbor here, we're going to plug in what we just derived up there. Okay? So same exact process that we've done before for these boundary conditions. The only difference now is that we have this additional term right here in the beginning to deal with. Okay? So eventually, what's going to happen is we're going to plug in for the west integral just like we always did. But in order to get the coefficients, what we're going to do is we're going to multiply it all by delta t divided by delta squared. Okay. And this is due to unsteady term. And so because we've discretized that initial unsteady term, we have this extra kind of coefficient that we have to float around. Okay. All right, so let's go ahead and do that. So if we do that and we apply that to one of the equations, so let's say that we're doing this for cell 5. Okay. So actually, I think in the when I first did this example, when I first drew the domain, I didn't draw the cells. So let me draw those again. Okay. So there's our 4x4 domain that we're working with. So let's say, so in the example that we just did with the Dirichlet boundary, we did that for a case where the west boundary was a Dirichlet. Okay. So that can apply basically to any of these guys over here. Okay. Because all of these ones on the left side here, they have a Dirichlet boundary on the left. So we won't do cell 1 because cell 1 is a little bit complicated because it has a boundary condition on its west and its south side. So let's do this for cell 5. So cell 5 is kind of a nice one because it has a north neighbor, an east neighbor, and a south neighbor. So we can leave those integrals unchanged, but the west integral will change because of the boundary condition. Okay, so then if we plug in all the numbers and we move things around, then we get the following. So this is the equation for cell 5 right here. So first thing we get is 10 cosine pi t minus 4.8 times phi 6. Okay. So 6 is going to be the east neighbor of cell 5. So notice how this term is kind of unchanged from our interior expression because we have an east neighbor. So the east integral is going to be exactly the same. Okay. So the same thing goes for the next term. So the next term is going to be our north neighbor. So that's going to be unchanged. So we have 0.2 sine of pi t, okay, minus 4.8 phi 9 at n plus 1. Okay. So that's going to remain unchanged. Okay. So at this point, we usually, our next integral would be the west integral that we would plug in for. But since we don't have a west neighbor, there's nothing that we can plug in. So we're going to skip the west, or not skip it, but we're going to, you know, after we plug in for, you know, that expression on the previous page, then we're not going to get an expression here. Okay. So I'll show you kind of how that integral kind of shakes things up. Okay. So then after the west integral, we have the south neighbor. So the south is also going to stay exactly the same. So this will be plus minus 0.2 sine of pi t minus 4.8. Okay. Okay. So the south neighbor for 5 is going to be cell 1. Okay, so that's where that comes from. Okay. And so next we have 25, phi 5 at n plus 1. Right? So notice how this is a little bit bigger than before, because if we look at our interior cell equation, okay, so our interior cell equation had this right here. Okay? So our interior cell equation had 20.2 at the center cell, okay, at n plus 1. But because we applied the Dirichlet boundary condition, that's going to increase this value because of this guy right here. Okay? And so because we have that Dirichlet boundary condition, that's going to increase the kind of the contribution from phi sub c. Okay? And so that's why we have an increased value here. So we have a value of 25. Okay? Okay? And all this is equal to, we have our source term, which is the same as before. So we have 0.3 xc yc, okay, plus phi 5 to the n. So that's remained unchanged. Okay, so that, remember, that comes from the time derivative term. Okay. Right, so this is so this first term right here comes from the Dirichlet boundary condition. So this is going to be our u delta t d naught all over delta squared. Okay. So remember, when we plugged in the Dirichlet boundary condition, we had one term with the convection velocity and one term with the diffusion. So this is the first of those. Okay, so we have u delta t times phi naught divided by delta squared, where phi naught, remember, is equal to 50 in this case. Okay. And then we also have a contribution from our diffusion term. So this is going to be 2k phi naught delta t divided by delta x squared. Okay. Right. And so this equation right here is the algebraic equation that results from applying the Dirichlet boundary condition to this unsteady problem. All right, any questions on that?
So for the corner nodes, I mean corner cells, we would have to replace two integrals and multiply the two boundary conditions by delta t over delta squared.
That's correct. Yeah. Yeah. So for the corner cell, so we'll do a corner cell next, or I'll show you kind of the answer for the corner cell, and I'll show you kind of every contribution. But yeah, you would have to replace two integrals there because they have two boundary conditions that you need to apply.
Okay. Thank you.
Mm-hmm. Yeah. Yeah. So let's do cell 4. So cell 4 is kind of in the bottom right corner of our domain. So that one has two boundary conditions. So I'll show you kind of how that kind of shakes up. Okay. Before we do that, are there any last questions on this guy here? Okay. So let's do cell 4. So cell 4 was on the bottom right. Okay. So on the bottom right, it's going to have a boundary condition on its south face and on its east face. Okay. So what this means is that we're going to replace both the south integral and the east integral. Okay. So if we do that, we get the following. Okay. So even though we're replacing the south and the east one, our west and north integrals are going to stay the same. So let me start out with those guys first. So first, let's do the north neighbor. So the north neighbor for cell 4 is going to be cell 8. So we have phi 8 at n plus 1. Okay. Then we have the west neighbor. Okay. It's going to be minus 10 cosine of pi t. Okay. Minus 4.8. Times phi 3 at n plus 1. Okay. Okay. Then we have our self. So this is plus 29.8 times phi 4 at n plus 1. So notice how the value of this coefficient is again increased because we have the contribution from 2 boundary conditions. So we've gone from 20.2 with no boundary condition to 25 with 1 boundary condition, and then up 29.8 for 2. So basically each time we're going to add 4.8. So it's not 4.8 every time. It's just 4.8 in this example, just because of the values of the coefficients. But you can kind of see how, you know, the contribution from phi sub c is increasing as we border more Dirichlet boundary conditions. Okay, so then this is equal to. So first we have our source term, so that's 0.3 xcyc. Right. Then we have phi sub c at n, so in this case that's going to be phi 4. Right. Right. So next we have 500 minus 500 cosine of pi t. Okay. And then plus 240. Okay. So both of these guys are coming from the boundary condition on the east face. Okay. And then we have a plus 10 sine of pi t plus 240. And these are coming from the boundary condition on the south face. Okay? So in both cases, you can see we have a sinusoid. So in the first case, we have a cosine, so that comes from u, right? So that comes from u because that's on the east face. So the east face is going to have, it's going to be governed by the horizontal velocity u. Okay? Then we have a plus 240, so the 240 comes from the diffusion term. Okay? So then to that, we're going to add 10 sine of pi t. So 10 sine of pi t, that comes from the vertical velocity, so that's v. So that's the v contribution. And then we have another 240 because that comes from the diffusion term. Okay? So notice the 240s are the same because we have a grid that has kind of even spacing in x and y, and both of those are going to contribute some diffusion term for the boundary condition. Okay. Any questions on this guy? Okay, so the next thing is we're going to jump into the MATLAB code, but before we do that, I kind of want to give you kind of the expressions per integral, okay? Because remember, the way that we implement these MATLAB codes for finite volumes is that we evaluate basically each of the integrals basically separately. So basically what you're going to see is inside our for loop is we're going to have an if statement that corresponds to the east integral, one for the north, one for the west, and then one for the south. Okay? So it kind of helps to kind of evaluate each of these expressions with the delta t over delta squared, so with the additional coefficients from the unsteady term, just so we can kind of just plug those straight into our code. Okay? So let me go ahead and do that. So let's do just the east integral, okay? Just as an example, and then you can kind of follow the same process for the other ones. Okay? So for the east integral, we have integral of east times phi v dot n, okay, minus k gradient of phi dot n ds. Okay. But in addition to this, we have to multiply by delta t over delta squared, because remember that comes from the unsteady term. Okay, so we're going to multiply this by delta t over delta squared, okay, where this comes from unsteady term. All right. So then if we apply our integration rules, we end up with the following. So we still have our delta t over delta squared, so I'm going to leave that out in front. So then we also have a delta. So remember, this delta comes from this ds right here after applying the trapezoidal rule. Okay. And that's going to be multiplied by u over 2 times phi sub e plus phi sub c, okay, minus k over delta phi sub e minus phi sub c. Okay. And so after we get it in this form, we can rearrange it because remember, we want this to be a little bit more convenient in order for us to plug into the MATLAB code. So we basically want just one coefficient for the east neighbor and one coefficient for phi sub c. Right? So if we do that, we end up with the following. So we get, let's do the east one first. We get u, and all of these are at n plus 1, sorry. I think I might have forgot to do that up there too. Okay? So it'd be u delta t divided by 2 delta, okay, minus k delta t all over delta squared. Okay. Phi sub e at n plus 1 plus u delta t all over 2 delta plus k delta t all over delta squared phi sub c at n plus 1. Okay. Okay. And so what you'll see is that we're going to plug in this expression for the left-hand side matrix. So that's going to go into the coefficient for A at my ID, comma East ID. Okay. Meanwhile, for A at my ID, which is phi sub C at n plus 1, this is what we're going to plug in for that guy. Okay. Any questions on this? Okay. So that's for the general case when we have an interior cell or we have an east neighbor. But for the case where we have a boundary condition, we need to change up our coefficients a little bit. Okay? So let's do the modified version of a Dirichlet boundary condition. Okay. So in this case, we have delta t over delta squared. Okay. So we have the same coefficient that comes from the unsteady term, and this multiplied by u b naught minus k d naught minus phi c all over delta over 2. Okay. So remember, that was the expression that we were working with before. Okay. And so if we plug this in and we evaluate it, we get the following. So we get 2k delta t all over delta squared times phi sub c is equal to minus u delta t all over delta plus 2k delta t all over delta squared phi naught. Okay. and this is n plus 1. So just like before, the coefficient in front of phi sub c, that's going to go into a at my ID. Okay. And then all of this, since they're going to be known values, this is going to go on the right-hand side. So this is going to go into b at my ID. All right, any questions on this before we jump into the MATLAB code? Okay, so let's go ahead and jump in. Okay, so this code is posted on Titanium, so you can take a look at that. Okay, so let's go through this kind of the same as we always do, right? So let's start with the first section. So this first section of the code is still the same as before. So here we define all of our parameters here. So we have the length of the domain in X and Y, and then we have the number of cells in X and Y. Okay? Then we have the total number of cells. We have this grid spacing. We create the data structures for the left-hand side matrix and the right-hand side vector. And then we also define some constant parameters. So in this case, since the diffusion coefficient is constant, we can go ahead and define it up here. Okay? So we have k is equal to 3. And then we also set our time stepping parameters. We have dt and n sub t. So notice how we didn't define our convection velocities. And then the reason for that is our convection velocities are going to change with time. So that's going to be basically the same as your project. So in the project, remember, for the starter code, I'm having you define the velocities within the time stepping loop. Okay, so the next thing is we have to define our solution variables. So first we have sol next. So this is phi at n plus 1. Okay, so we're basically just creating a container for it. So that's why we use the zeros function. Then we have sol cur. So sol cur, that's going to be our current solution, and that's phi at n. Okay, and since we're starting with the 0 initial condition, this is what we're going to use for. Okay, next, so next thing, I'm going to create a video. So this is just like in the project. So you don't have to worry about this code, but it'll work for you. Okay. And then from here, we jump into the time stepping loop. Because for every time step, for every unsteady problem, remember we have to have a loop. Okay. So this is our time stepping loop to go over all time steps. And so the first thing we do inside our time stepping loop is that we compute our convection velocity. So you can see we have u and v here. Okay? So since they're functions of time, we have to basically recompute these at every time step. Okay? So this is just like you have in the project. Okay. And so the next thing that we're going to do is we're going to reset our left-hand side matrix and right-hand side vector. Okay? And the reason for this is because basically at each iteration of the time loop, we're going to add the coefficients. So we want to make sure that we reset it each time so that we're kind of starting with a blank slate. So we don't want the coefficients from the last time step to affect this current time step. Okay. So we do this so that coefficients from the last time step do not affect this current. Okay. And so from there, we enter into more loops. So we have loops on loops on loops. So this is kind of a triple nested for loop here. And remember, the purpose of this for loop is to visit every cell. Okay? So these loops are a bit different. So notice how they're loops over nx and ny. So these are loops that kind of loop over space. Whereas this time stepping loop up here, you can think of it as a loop that progresses over time. Okay. Okay. So the next thing that we have is we compute the ID numbers. So we have the ID numbers for my ID, West ID, East, North, South. Okay. So this is the same as we always do. So we have to compute the kind of the indices for each of the different ones. Okay. So my ID, remember, this is going to be the index for phi sub c. West ID, this is going to be the index for phi sub w. Next, we have east ID, so this is phi sub east. North ID, this is phi sub n. And then south ID, this is phi sub south. Okay. Okay. And so from here, we have the, we jump into each of the different loops, or each of the different if statements, sorry. Okay. So you can see here we have the east integral first. Okay. So for the east integral, we have if I is equal to nx. So this first part of the for loop is that if we are at the boundary. Okay. Or in other words, another way to say this is that we have no east neighbor. Okay. So if we have no east neighbor, then we jump into the expression for the boundary condition. So you can see here we have a at my ID is equal to a at my ID plus 2k times dt divided by dx squared. So that was the value of the coefficient of the expression that we just had kind of before we went to this MATLAB code. Okay. And then besides that, then we also have to modify our right-hand side. So our right-hand side gets modified by our traditional boundary condition, which is 25. So 25 is the value of phi naught, phi sub 0. And then we also have our other coefficients here. Okay? So then the flip side of this if statement is that if we're not at a boundary, then we have an east neighbor, or we're facing an interior. Okay? So there is a neighbor to our east. So if there's a neighbor to our east, then we can apply the coefficient that we saw before. So there were two of them. So first we had a at my ID. So this was the coefficient in front of phi sub c from the previous lecture slides. Okay. And then we had the coefficient at a at my ID east ID, and this was the coefficient in front of phi sub east. Okay. So if you match up these coefficient expressions with what we wrote down in the notes, you should see that they are the same. And then you can basically do the same things for the south, the west, and the north integral. So I'll leave that to you guys to verify. Okay. But are there any questions on this, just the east integral? Okay. So the other thing that you have to be careful of here is that you have to be careful of the signs of these guys. So it can be tricky. So especially the signs of u and v. So in this case, we're performing the east integral. So we have a negative out here and a positive over here. But for the south integral, you can see here because that's on the bottom side, and our normal vector is 0, minus 1. Then we multiply everything by minus 1. So we have a positive v on the right-hand side for the boundary condition, and we have a minus v right here for the interior cell. So just be careful about the signs of those convection terms. Okay. And so the other things that I want to highlight here are this line. So this line is a little bit inconspicuous, so it's a little bit easy to miss, but it's really important. Okay. So we have to add a coefficient of 1 to the diagonal. Okay. And this comes from the unsteady term. Because remember, when we discretize the unsteady term, we have a phi sub c at n plus 1. Okay. So if you kind of go back to our general expression for the interior cells, we can see that we have a plus 1, so that one's right here. Okay. And then the other thing that's a little bit easy to miss is that we have to account for our source term. So that's what this guy does right here. So our source term is going to be 3 times x times y times dt. Okay. And then we also have to add this. Okay. So this sol cur at my ID, this is the same as phi sub c raised to the n. Okay. Let me do it like this: phi at n sub c. Okay. Because remember, when we're doing implicit time advancement, we get extra phi terms from that time derivative. So one of those phi terms goes on the left-hand side, which is phi n plus 1. So that's what this guy is right here. Meanwhile, we also get a term on the right-hand side for phi at n sub c. Okay, and that's what this is. So when you're doing implicit time advancement, I think these two are really easy to miss. So make sure you don't miss those guys. Okay. All right, any questions on this? All right. So let's go ahead and run this code. Oh, question. Let's see. Is there a dt squared in the B? Let's see. There should only be one dt because you only get one dt that comes from the time derivative. So when you multiply that dt through, you should only get one. So you would get a dt squared if we had a second time derivative. So say if we were solving like a wave equation. But in this case, since we have just one time derivative, there should only be one dt. Yeah. All right. So let's play that video again, just to see it again. So it's kind of a cool animation. So it basically looks like a membrane that's kind of pulsing back and forth. So actually what this reminds me of, just kind of a little bit of a preview for Wednesdays, this kind of reminds me a little bit of kind of your heart wall when it's kind of beating back and forth. So your heart kind of is beating all the time. And this kind of reminds me of that. Okay. So that's it. So, you know, maybe this is anticlimactic or not, but this is, you know, basically all the content that I had planned for this class. So we ended about 15 minutes early, so not as much as I thought, but so that's, you know, computational heat transfer for you guys. So since we're ending since we're done with kind of all the content a bit early, kind of as we talked about last week, the plan for Wednesday is to just kind of have a research seminar. So I have some lecture slides planned where I've kind of, you know, just kind of showcase some of the previous work that I've done. So just kind of a nutshell, but kind of the work that I've done before was I've used computational simulations that are very similar to this. They weren't implemented in MATLAB, but they were implemented in Fortran. And I used that to study or to simulate blood flow to kind of do some research around that. Okay? So if you're interested in kind of seeing what that's all about, then all you have to do is just tune into our regular lectures on Wednesday. But by no means is it required material for the class. So, you know, if you have to study for other exams or you're working on other projects, then definitely, you know, you can, you know, work on those things. It'll be recorded just like always, and I'll post it on Titanium. But if you're free during that time and you want to kind of check that out, then you can definitely tune in. Okay? So with that, you know, I know we still have a little bit of time, so I'll stick around until the end of lecture. But that's all I got for today. So I will see you guys on Wednesday. Yep. Yes, yeah, so I'll still have office hours this week. I'll have office hours next week too. So even though next week is finals week, I'll still have my regular office hours. So you can come in and ask questions. But if the office hour times don't work for you, then just let me know. Because I'm literally sitting here like, you know, almost 15 hours a day. So you know, I'm always free to kind of meet up whenever you need to. So if there's a time that works better for you, just send me an email, and I can create a Zoom room for us to kind of chat about anything. Sure. So office hours. So I had office hours today from 9 a.m. till 10:30. So that's the Monday office hours. So that's in the morning. So Tuesday office hours are in the evening. So Tuesday office hours are from 5:30 p.m. until 7 p.m. And then Wednesday office hours are in the afternoon. And that goes from 1:30 p.m. until 3 p.m. Yeah. Mm-hmm.
Yes, I have a question.
Sure.
Can we go back to do you mind going back to the corner cell? Cell
Sure.
4?
Yeah, let me connect my iPad again. It kind of went to sleep on me.
Oh.
Let's see. Okay. think it was this guy, right?
Yeah. So my question here is, when we did the single dirichlet boundary condition, you added a west integral in parentheses.
Yes.
And for this corner cell, you didn't add an east and south.
Yeah. So I think maybe that was a little bit confusing. So that I kind of put that there as I kind of meant that to be kind of as a blank, because that's kind of normally where we put the west integral, but here it's kind of blank because we're kind of replacing it with the Dirichlet one. But for this one, you can kind of imagine that there's kind of blanks where you would put normally the east and the south integral. So
oh, okay, yeah.
So in this one, the west integral isn't actually there because we've already kind of included it, but kind of in the normal case where we'd have an interior cell, that's where it would go. So this is kind of like a blank where it would be normally.
Okay. Yeah, I just confused myself. I went to go get some water and came back and playing catch up on the notes.
I see.
Okay, thank you.
Yeah, no problem.
See you on Wednesday.
Yep, see you Wednesday.